Assalamu alaikum. In this lab session we will be performing example 1.6, torsional spring constant of a propeller shaft. As a part of the lab session, whose detailed statement will later on be sent, but for the time being you can say that this is the application of the torsional free vibrations which have been demonstrated in the previous lab session in the article 2.3, free vibrations of an undamped torsional system. So the concept of this article will be applied to this lab session. So here it says that determine the torsional spring constant of a steel propeller shaft shown in figure 1.30. This example we have covered it in theory part, but now we will be modeling its geometry in ANSYS model module, and this propeller will be created as the rigid disc, means the end mass, and these two hollow rigid shaft portions, which are actually the springs in series, will be treated as the elastic members which have been connected end to end in series. So let us first launch ANSYS workbench, and what will be the methodology that we will first of all be actually creating this model as it is given, and after that we will also be verifying it using the equivalent stiffness system. So let us first create the geometry. Just start a model module, and having started, click on geometry cell A3, so at the same time you can observe here it has given two sections, section AA and section BB, for these two portions of these shafts. One portion of the shaft has length 2 meter, which is connected to the stationary surface, and the other portion of the shaft which has been connected in series with the this left portion. So its length is 3 meter and its internal and external diameter have also been shown here. So we will be creating these portion as the line bodies. Actually we can also create as the solid bodies, but for the time being we will be creating it as the line body. So click on XY plane and click on Z axis and go to sketching and click on line, and suppose this is the stationary surface at the origin at this location. So now the dimensions are in meter, so use 2 dimensions and dimension this segment to be 2 meter as given here. the left portion for the shaft. Here this is 2 meter, and again here important thing is that as we can observe here, that these two portions of the shafts have been are made of the same materials, means the material of creation for these two shafts is same. This we can verify it from here, as the value of G modulus, shear modulus, this is 80 × 10⁻⁹, which is same for both portions of the shafts. So that means the material is actually same, because the torsional stiffness is same. So if the value for G were different for a given portion, then we would have to create two different materials, means this line segment of 2 meter will be created as the add material property, and this second portion, for example 3 meter shaft portion, will be created as the add frozen property in using two different sketches. But for now, because the material is same, the value of G is same for both portions of the shaft, so we can create them using a single sketch. So let us create the next portion. Here you can also move the dimension a bit closer for better view here, and like this, and now create the next line segment. Yes, again very important, the value of G also matters, but now as the sections are different, because the sections are different, internal and outer section dimensions for both portions of the shafts are different, so we cannot create the single sketch. So either the value of G is different, or the values of the sections are different. In every case, we must create two different materials or two different portions of the shaft, or two different sketches. So just escape it, just finish it, and here you can first create it an independent line body, and just apply it. And because if we had created these two shafts in the single sketch, we could not assign the different cross sections to each portion of the shafts. So to avoid this, we will be creating them independently. So create this line body, and now click on concept and assign it the cross section, and cross section must be circular tube, because circular tube cross section, because this is the hollow section. So give its dimension to be here like this. This is the R outer. So first change the R outer inner radius, and remember here that as we can observe here, this is the diameter, outer diameter. So outer radius will be half of 0.3 meter, so that will be 0.15. So what you can do, that this will be R outer, sorry, first change R outer to be 0.15, and then change the R inner is a 0.2 diameter, so 0.1 will be its radius. So its radius will be its radius will be 0.1, like this. So after that you can just assign this circular tube, and also click on cross section solids to visualize the section dimensions, just for visualization purpose. So like this, and you can now set the planes off and again zone fit. So this this left portion of the rigid shaft, this elastic shaft, this is the elastic shaft, torsional rigidity. This is not the rigid shaft, this is the elastic shaft. So the disc is rigid because this is the end mass. The shaft is not rigid, remember. So this has been created. After that, now create on the same plane, XY plane, create a new sketch. Because why new sketch? Because the sections are different for these both portions of the elastic shafts, and also material is though material is same, so either the material were different or the sections are different, we will have to create two different sketches, and we will be creating them using add frozen property. So we have used the add material property for this portion of the shaft. For the other portion we will be using add frozen property. Now click on sketch 2 and go to sketching. In a similar manner, click on this, and now create the next portion. So click on line here and from here. So as you can observe here, that its dimension is 3 meter. So give its dimension to be 3 meter here. Just change it to be 3 meter, like this. And now again click on sketch 2, go to concept, go to concept and click on line from sketches and apply it, and remember, put it add frozen. This is very important. Put it add frozen and click on concept and click on cross section and click on circular tube, and now change its values. So as we can observe here, that the outer is 0.25 and the inner diameter is 0.15. So its radius will be 0.25 divided by 2, which comes out to be 0.125. So the outer radius here is, as you can observe, outer radius is to be 0.125 and the inner radius is 0.15 diameter. So 0.15 divided by 2, this comes out to be 0.075 0.075 like this. So again assign this portion to be, and like this the geometry has been created successfully using line option. Remember, this is the line body. We can create the geometry for these both portions of the shaft as to be solid body, means the extruded material. So that can also be attempted, but for the starting case I have used the line bodies. So the geometry has been created. Now the next important thing is that we will also be creating this rotor portion, which be created as the solid rigid disc. So just for as a purpose of visualization, we can create as a solid rigid disc, and we can create that rigid disc to be as the solid disc. For example, what we can do, we will first of all be setting a plane parallel to this YZ plane, So first create a new plane here and set its type to be the base plane, the type type is to be from plane, and the base plane is to be YZ plane. Remember, because the new plane will be parallel to this YZ plane, because at on this end like this. And now what will transformation be? Transformation is to be global along x-axis. It means offset global. Remember here, offset global x like this. And how much? Remember here 2 plus 3 means at this point 5 meter. So put it to be as a positive 5 like this here at this portion, and click on generate here. Now on this plane, actually this plane 4, you will be creating the new sketch here, and you can for example select x-axis as to be, and here you can create a for example circle, just a visualization for the rigid disc. So assume its dimension to be, for example, its diameter to be this. So put it unity, for example, unit diameter, and after that we will be actually extrude it to be point 1 meter, for example. That is sufficient, and click on generate like this. So in this way, as we can observe here, total 3 bodies have been created, 2 line bodies as the elastic shafts portions in series, and one is the solid and rigid disc. So the geometry has been created, and after that we will be clicking on model cell A4. The geometry has been imported. Now first of all we will be creating defining the materials. Remember, we will again be creating these shafts to be massless. Remember, these shafts will be treated as to be massless, zero mass, because these are actually the massless springs, means massless elastic elastic parts, and only the end mass will be considered, as we are familiar. So but remember, the value of G is to be verified. Here click on engineering data, and here you can observe the value shear modulus here given is 7.6923 10 raised power 10. But here in our example, as we can observe here, for both portion of the shaft, the value here given is this 80 10 raised power 9, mean, for example, you can say 8 10 raised power 10. So change this value to be exact. But here, as we can observe, that this shear modulus is actually not available. So remember, in engineering data, this is very important when for example this is structural steel, and here we can observe here that the Young's modulus is generally available. Young's modulus, actually this is used for tensile or compression or bending cases, and Poisson's ratio, this is the default value. But bulk modulus and shear modulus, remember, as you can observe, bulk modulus and shear modulus are unavailable. So how to make them available so that you can change them for the torsional models? So what you can do, you will click on here this on 7th cell, 7th row, derived from here, and you will be selecting from this list as the shear modulus and Poisson's ratio, this. So or you can select this shear modulus and Young's modulus extra, because Young's modulus here is not important. Here important is shear modulus and Poisson's ratio, like this. So you can change it here, and it is in Pascal, means Newton per meter square. So now you can change it here as to be, for example, you can simply type 80 E 9, 80 E 9. So 8 10 raised power 10. Here you can observe 80 multiplied by 10 raised power 9, so 8 multiplied by 10 to the power 10. Hence the value of shear modulus has been changed, and this is same for both the portions of the shaft. So in this way you can change the shear modulus. So this is very important for the torsional models. And After that, in a similar manner, you can put the density for the shafts to be, for example, in a similar, you can say 1e minus 20 in the similar manner as we have been already using. So the density has been said to be negligibly small to make the elastic portions of the shaft to be massless. So again we will also be creating another material for the rigid disc. So we can just, for example, duplicate this material as to be, put it as duplicated, and name change it means rotor. You can say type it, for example, rotor or end disc or end mass here like this. And again for this rotor you will be creating for example, you have to create a unit mass. So later on we will be creating its mass here. Now go to now click on this line body and assign it the structural steel default material and check on its properties. First of all, you can refresh materials, and now click on this line body and check its mass is very small, means negligibly small here like this. This is also very small. And on this solid here you will be selecting the other material as to be this rotor, and here you will actually be what, for example, you are assuming the mass is to be unit, means 1 kilogram. So its volume as given here 7.854 10 is power minus 2. So if the unit mass is to be there, so we can simply be mass per unit volume. So the density will be calculated as 7.854 divided by, so the density comes out to be 12.732 for the unit mass of the end disc. So you can put it to be the density for the rotor to be 12.732 like this. And again now refresh materials, and now click on this solid disc, and now you can check it here that its mass is has been unit, means 1 kilogram. So as you can observe here, the lines are line bodies are massless, and this end disc. And after that you will be creating the connections, and connection will be between these two shafts because they were of different materials. So what you can do, for example, just make it off and hide body. Just hide one portion, one shaft, and click on here joints, and in click on connection, insert, and click on joint, and joint as to be as the fixed body dash body, and for example, for reference we can select on this point filter as to be this point. And now what we can do, that we will be clicking on show all bodies, and now we will be selecting this body and make it as hide body, and again go on here and click on point filter like this, and click on apply, and as the fixed joint has been also placed. And remember, another fixed joint will also be placed between the rigid disc and the rigid end disc and this point. So we can place them, for example, like this. Click on joint, insert new joint as to be as the fixed joint, body dash body, and for reference, for example, we can click on this point of that line end, and after that we will be the second body as to be, for example, the face, and we can just like we can rotate it here like this, and now we will be clicking on this face as to be, this face will be connected with this end point as the fixed joint. So line to solid, so the joints has been created, and after that we will be for putting the analysis setting, the mode must be 1, and now what we will be doing, we can clicking on we will be applying a fixed support. First of all, geometry, show all bodies, and on on this point click a fixed support, apply it, and after that what we will be doing, that we will be putting the remote displacement like this, and here on this face, on this circular face, we can select just this face, and we will be putting here in this face is located in YZ plane, so x must be constant because no deformation, and y and z must be free, and rotation about x must be free. Rotation about x and rotation this must be rotation in z, that must also be 0, and the behavior must be rigid for this shaft. And this, now click on this insert deformation, total deformation, and now just solve it and see what happens. If there is any problem, we will be investigating for where the error is located. So here, as we can observe here, for the frequency here, it comes out to be 351.08. Here here we can observe that there is a problem. We will because this disc must be rotated. This is not actually rotating, so let us investigate this problem. So the issue has been actually investigated. The reason was that in the remote displacement, remember here initially the setting here was that we actually set that this disk is actually in YZ plane. Remember, this disk is in YZ plane and this disk is in pure rotation. So initially in the previous case we had put y and z to be free, linear, means y and z linear parameter were set to be free, but these must be 0. Remember, these must be 0 because this disk is in pure rotation, so that actually creates problem. So only rotation about x-axis, means the x-axis is actually is the polar axis. Here for this disk the perpendicular axis is x-axis and this is the polar axis, because the rotation is not possible in the axis y and z, because this disk is actually containing those axes. These two axes x, y and z are actually located or in the planes of the disk, in the face of the disk. So this polar axis, which is actually perpendicular or along the shaft axis, this must be free, and rotation about, as we can observe here, yz must be 0. So actually this was the reason for previously. So remember, for the end disk you will only be putting the polar axis rotation in the polar axis to be free, and all linear parameter will be set as to be 0. So this will solve the problem. So only this was the reason. As you can again observe here, if I am putting, for example, y to be free and z to be free, so again I am solving it. So as you can observe it here, so this was the reason. As we can observe here in the previous case, actually this was moving like this, so that was incorrect. So if you change the remote displacement setting as to be all linear to be 0, because the disk is in pure rotation. This is the rotational inertia, and only the polar axis, which is the x-axis which is perpendicular to this phase, and the behavior is also rigid. So this actually creates solve the problem. As you can again solve it and verify it. So here, as we can observe here, the value, this comes out to be 1207.8 hertz. So we will now be verifying this frequency using this formula. So the value for the frequency, linear frequency, is kt by j naught. And remember, the formula for j naught, as we are familiar, this is given on the next page here, wd square by 8g. So w by g, you can say it to be the mass, which has been assumed to be 1 kilogram. So m means the formula is actually j naught. The formula for j naught is md square by 8, and this has been previously discussed that here must be wd square by 8. So this is correct formula, because for the rigid disk, this is the formula for mass moment of inertia. So md square by 8, and d has been assumed to be 1 meter, as we are familiar here. As you can observe, I had told that the sketch 3, for sketch 3, diameter was chosen to be 1 meter. So the diameter was used to be 1 meter. So md square by 8 means 1 by 8 simply. So when you will be calculating this value using this formula, you can yourself calculate, but I can help that j naught, the value of j naught comes out to be 1 by 8, means 1 by 8, this comes out to be 0.125, and take its reciprocal and multiply it by kt, and the value of kt is actually calculated here. This is the equivalent torsional stiffness. So this is 6.597 multiplied by 10 to the power 6 Newton meter per radian. So multiply it by 6.59997 multiplied by 10 raised power 6. So this comes out to be 52797,600. So this is the value for the equivalent torsional stiffness. So just take its square root, and this comes out to be 72 66.1957, and now you can divide it by 2 pi, so divide it by 2 and divide it by pi. So this comes out to be the answer which I got is 1156.45, means 1156.45. So here the value which the software gave is 1207.8. so if we compare it with the theoretical value and compare its percentage error, we can observe, because the theoretical value is actually ideal value, so we can just take their modulus difference. We can minus 1207.8 and divide it by the theoretical value. So the error, percentage error, comes out to be 4.44, means only 4% error is there. So for the graphical or iterative work, means this FEA work, the error about 20%, means 18 to 20% error is allowed. So the error is very small, and you can observe that the results are closely matched. So hence the problem has been solved. Our next task is the verification by creating the equivalent system. So let us now create the equivalent system for the same system so that we can verify it. So what you can do, that you will be inserting a parallel module here like this, and you will again be creating for the engineering data. You can at this stage you can again set that you will have again to create two materials, one for the elastic shaft and other one for the end disc. So just duplicate it and rename it. For example, this is the equivalent rotor, you can say equi rotor. And for this structure we can rename it to be for the shaft, and the shaft must be massless in a similar manner, so put it 1e minus 20, and again it's remember the shear modulus like this, shear modulus and Poisson's ratio, and again put it 8E 10 8E10 and for the rotor we will be again using the same density with 12.73 etc., the same value which we had already used. The same value here that we had used here, that was actually 12.732. so 12.732 again the same, and like this, and now create the fresh geometry for the equivalent system. Here again fastly create just create a line, give its dimension to be, for example, you can create just a unit length for this shaft, and like this, and now click on here, click on sketch, create concept line from sketches, and click on generate. Line body has been generated, and after that assign it a cross section, and remember the so at this stage this is very important, so that what will be the what type of cross section is to be used for the equivalent shaft. So remember, we can use the solid circular shaft, so click on here, and here it is important what will be its radius or diameter for this shaft. So for this we will be taking the assistance of this equation 2.39. Here the formula for KT is given it here, pi g d raised power 4 by 32 L. So what will be the value of KT? We will actually be using this equivalent KT and this KT, this equivalent KT 6.5997. so we will be actually creating here, because pi and g are constant and length has also been already selected is to be 1 meter. So we will be actually calculating the value of this diameter. This will be the diameter, equivalent diameter for the a shaft having length 1 meter. So this value you can calculate it yourself. So I am again assisting that the value chosen for the length is 1 meter. So that means the value we can calculate it here, that KT is actually 6.5997 6.5997 multiplied by 10 raised power 6, and we will be multiplying it by 32. KT multiplied by 32, length is 1 meter, and now we will be dividing it by pi, and again we will be dividing it by capital G, which is the shear modulus, and the value for this is actually 80 10 raised power 9. So divide it by 80 and divide it by 10 raised power 9, and now take its 1/4 power so the value of diameter which comes out to be according to my calculation is 0.17 0258 etc. So up to 2 decimal if we use it, this comes out to be 0.17. so just use 2 decimal. For more accuracy you can use more decimals. So here the value is 0.17. Sorry, this is the diameter, so the radius will be divided it by 2. So this is 0.8085 129 up to significant figures 0.085. You can use only 3 decimal places, but I have used here 3 more decimal places for better accuracy. So now you can assign this cross section and click on its visualization, how it looks like this. And now in a similar manner insert a parallel plane at this end, parallel to YZ plane like this, as we had already placed in the previous model. Click on new plane and diaphragm plane, and the base plane should be YZ plane. Apply it, and the transformation must be global x-axis, offset global x, here offset global x, and put it to be 1. So here this plane will be created, and now on this plane click the sketch and the disc of same dimensions as we had already created. That click on, for example, circle, and click on it here, and its diameter, give its dimension to be diameter unit 1 meter diameter like this, and click on create extrude, and exactly the same as we had already created, uh, for example 0.25 I think we had created. We can again check it out here that the extrusion sorry, it was 0.1 meter, so also put it 0.1 meter so that the same volume has been generated 0.1 meter like this, and click on generate, and in this way. So the equivalent model has been created, and after that what you will be doing, that click on model cell B4, so here again the connection will be made for first of all check its properties, and here as we can observe its properties, that this is massless, and for the solid and disk we are observing that we will be its material must be this equirotor, and here we can observe it its mass is same unit kilogram, because the material properties were already set. And now place the connection between the shaft, because there are two different materials. So click on joint, and simply click on it here like this point filter, and click on this point, and after that click on the shaft, and just we can for example just rotate it here like this, and after that we can click on this face, and this face will be connected as a fixed joint with this end, and after that analysis setting to be one mode, because single DUF, and after that what we will be doing, that we will be applying a fixed support at this fixed end of this shaft like this, and after that we will be putting on remote displacement as to be upon this face, and again similarly only all parameters will be 0 here except the polar axis, which is x-axis, which will be set as to be free. Rotation x must be free, because this is the polar axis. Remember, this axis should be wisely selected, and the behavior is to be rigid like this, and now click on the total deformation, and now try solving it and see what happens. and hooray, we have uh, achieved the same result. As you can observe here, that in the previous case our result was 1207.8, and the equivalent is more accurate as compared to theoretical values, because the theoretical value that we had calculated, if you remember, yes, that value was 1156, and here this is 115.3. so in this way, as you can see its simulation as well. And remember, here, as you can observe here, and you are also observing the this twist of the shaft as well. Then this is also clear, as you can observe it by zooming here. The twist is also clear. So in this way, equivalence has also been verified, and this way this lecture, so student will be assuming a similar data, a similar model will be given for their assessment. So hence this way this lecture has been completed, and please mark your attendance and perform it similarly. Thank you. Regards. Assalamu alaikum.